Bonjour tout le monde. Hi everyone. So this workshop will be fully in English. We are really happy to have Intel coming here at 42 for their first workshop. They have launched a new SDK for deep learning, and they will explain you how to use it in 1 or 2 hours. But we'll have a theoretical background and the speakers coming. So you have Florian, who is program manager, and Susanna, who is the engineer at Intel, that will do the first part and the workshop. So, yeah, Florian.
As you can guess, I'm from Germany, working in Munich at Intel. I'm a program manager. I'm not too technical. I always like to call myself the booth babe of Intel. I get sent to conferences and speak about the technologies. Therefore, we have we emancipated, and we have Susanna as our engineer here, who's going to be talking about the technological part of this. We're very happy to be here. To be honest, you guys are our guinea pigs, because you are the first stop for Intel in a 60 workshop roadshow throughout Europe over this year. So we're very excited for your feedback, for your perspective on the AI content. It's surely a technology that is going to change the way we live within the next 5 to 10 years. I think personally, over 180 degrees. It's a topic that everybody is talking about at the moment, and therefore we do not want to be the only company not talking about it. So therefore we're very glad to be here. At the end of the theoretical and hands-on piece, I'm going to introduce a program called the Intel Student Developer Program for AI. That's the methodology of how to interact with us. So if you say, hey, the content was interesting to us, the tools introduced seem like something we would like to use, the call to action comes at the end. I'll explain the program, how to engage with us through the ambassador program or the university club program. Both have a possibility for you guys to actually use Intel clusters to test algorithms that you might be developing over the next years or month, and have the possibility to engage deeply with Intel engineers on the topic of AI. With that, I don't want to beat around the bush anymore and stop the marketing pitch and actually hand over to Susanna, who is going to give I wanted to quickly run through the agenda. So you guys, as a German, obviously I love agendas and love to stick to agendas. So yeah, you heard the quick welcome from Jules. You heard my quick overview of why we're doing this. We're going to have Susanna talk about what is data science and machine learning. Then we're going to have a great guest speaker whose name is Jean-Christophe Bailly. He's here with us, and I don't know if he's in the room. He's sitting down there on the floor like a real CEO of a company, supposed to nowadays. Then we're gonna have a quick break. We're gonna have a little social challenge. So you guys, if you have Twitter or Instagram and you wanna tweet out about this, we're gonna have. We're gonna look at some of the tweets, and we've got some Bluetooth headsets. Intel generally has always the best swag. So we're going to have a bunch of those. We're going to give away. I'm going to look at your tweets and Instagrams. I don't know what the actual verb for that is. Then we're going to continue with the Intel Deep Dive technical training. That's actually where we're going to be hands-on showing the new Intel Deep Learning tool. We're going to show you how to set that up. We're going to have some sample data sets so you guys can get some first hands-on knowledge on that. And then afterwards, we encourage you to stay with us. I'm going to talk about the program a bit, explain the gives and gets, how to engage with us. And then from 5:15, we're going to have what all university students want. I always call it beer and pizza, and then also the possibility to come up to talk to us, to Susanna, if you have any questions, if you want to, propose some projects, some ideas, or just want our insight, or just want to share some things with us. Feel free to do so, and yeah, we'll probably close the gates at 7 because we had an early flight at 6:30 this morning and have a late flight this evening. So all for you guys. With that, now finally, this is the hashtag if you want to tweet something out, Intel AI, on Instagram or on Twitter. So again, we have a bunch of this stuff. Would be happy to see some interaction there. Yeah, with that, now the marketing stuff is over, and I can give the mic to Susanna.
So, hi, like he already say, I'm Susanna. I've been working in Intel for over a year now. I'm a developer also. I'm finishing my master thesis in computer vision and image segmentation. So even if this topic is not going to be exactly about computer vision, it's what I've been focusing the more, so I'm going to talk a little bit about that. Yeah, I've been a developer for some years. I've been focusing most of the time in computer vision and computer graphics. And besides that, my little secret was that at some point I was a Windows developer, which I am not proud of that, but you have to do what you have to do. So I'm going to talk to you now about what is data science and machine learning. So I just want to know, how many of you have any experience with machine learning already? Can you? Okay. So I'm going to cover like the basics, and then I'm going to do the workshop later. So I encourage you to all to stay, because there's where you will be able to see real time how fast a network can be when it's optimized. So this is going to be the general agenda. I'm going to talk about what is data science, and then I'm going to focus in what is machine learning, and 3 of its more important pillars, which is supervised learning, unsupervised learning, and reinforcement learning. So what is data science? Data science is it's basically the science of extract information from a lot of data and treat it with some techniques, and you can that allows you to have some useful information from the data. So that's basically it. It is very used now because we have so much data nowadays with the internet and with IoT. So machine learning and AI is not new at all. It's been developed so many years ago, but it never reached its full potential because of variety of reasons. One is we have much more data now, and the more data we have, the better we can use it with machine learning. And the second of it is that it is very, very you need a lot of processor. So you have to have very sophisticated computers in the past to do the things that we can do now with most computers. So we're going to talk to you a little bit of how to optimize it, and so you can have a better result. So how hot is this market? This is very, like I told you, it's not new, but it's emerging so quickly. In January of this year, we checked in LinkedIn, and it was over 9,000 opening for jobs for AI. And in another website called Indeed, it was 11,000. I just found this less than a week ago. And if you go to the Gartner site, it's over 41,000 openings for AI, while the experts remained around 50. So you can imagine there is so much lack of people that can do that. It's crazy. There is no one who's doing this. So it's the best moment for you guys to really start learning about this, because you guys are going to be super useful in the future, if not now. So what do you need to be a data scientist? Is obviously you need some hardcore things like Python and Erl, which is a new, not that new, but a little bit, programming languages. You need a very solid background in mathematics, specifically in statistics. You need to have a very big passion for data and to find hidden patterns in big amounts of data. You have to have like a storyteller and visualization mindset, so you can be more creative and can find better patterns on it. So just keep it in mind. This is the thing you have to develop so you can be a very good data scientist. There are many ways that you can approach AI. AI is very big. Also machine learning, which is already a subset of AI, but all of them will follow this pattern. So you have the reality, And from the reality, you will collect data. This data is raw data, and it's important that we define that it's raw data because it's important that we clean it later and we make some processing to the data. If the data is not clean, it can give bad results or simply be too time-consuming. So it's important that we collect the data, we process the data, and we clean it. With that, we can apply models and algorithms that I'm going to explain. And with them, we can have data analysis. So I'm going to explain some models and some algorithms, but keep in mind that AI is a very broad field. I cannot go through all, but just remember that if the things that I talk now, you think it's not the best for your problem, you have to remember that there are so many more. So maybe something out there, it's better for you. So that is data science. And a subset of it is machine learning. And machine learning is the field that studies how to give computers the ability to learn something without being explicitly programmed. So far, if you want to do an application, you write the code of what you expect the machine to do. But machine learning, what it tries is that you give a lot of data, and by itself, with some algorithms, will find the right result. So this is the pipeline for machine learning. You have the data. You have your machine learning model. I'm going to explain some of that. And to that model, you apply an algorithm. I'm also going to some of them. And then with that, you're going to have your output. Like I said before, when I explained to you how data science works, this is broadly how all machine learning will work. Doesn't matter which kind of machine learning it is. It will always has a model and algorithm every time. So in the case of machine learning, there are 3 pillars for it. There is supervised learning, unsupervised learning, and reinforcement learning. I'm going to go through all of them very detailed later, but to give you an overview of what they are, supervised learning. In supervised learning, you have all your data, and you have to label the data with what that particular amount of data is. So you have to do a lot of things manually to label the data. In unsupervised learning, you don't know much of the data. You just have a lot of information, and you have to find patterns on it, but you don't know much. So you just have to find something useful from that very big stream of information. And reinforcement learning is used for agents to maximize their performance in an environment. Maybe all of this is a little bit confusing, so I'm going to go through all of them detailed. But yeah, just remember those things. So in supervised learning, we feed the model with correct results. We give the model the data, but we also have to provide the model with what we know is the truth. This information of the truth is the label. And it's also called ground truth in machine learning. So if you see these words here, that they relate to the fact that you have to give the model always the truth. It is very used for classification. So you give your model a lot of data, you label the data, and then you give your model new data, and the model has to find the classification. This is an example. So you give your model all of these pictures. We all can see that in the top there are cats, in the middle there are dogs, and in the bottom there are birds. We know that, and we have to label each picture with the label. This is a bird, this is a dog, this is a cat. We train the model with this information. We keep showing pictures to the model, and we keep telling the model what this is. This is a cat, this is a cat, this is a cat, a lot of times. And then when we think, yeah, okay, maybe you are ready to recognize a new animal, we give a new picture to the model without any label, and the model and the algorithm has to find what this is. So in this case, I don't know if it's a dog or a cat, but hopefully the AI will know it for me because I have no idea. So how does that work? Because it sounds very good, but how does that actually work? So you have your data, and you have to plot it at some point. Because we have to label the data, I just made this simplification, and I put just these little images for each point of data. But in reality, it would be just plots. It would be just dots. So you show this to your model, and your model have to find that, these planes here. So the goal for our model is to successfully find those planes. Because with those planes, we can divide the data and we can classify it. As you can see, there is mistakes somewhere. This is okay because you have to remember that machine learning is not about getting the perfect result, but it's always an approximation. It is always using what is statistically more likely. So this is what you have to find. Of course, you might say you can create a more sophisticated equations that will yield this result. You can. It will take you more time, but of course it's possible. But even if you think that's the right thing, it's actually very bad and can give you one of the biggest problems of machine learning that is called overfitting. You have to be very careful because this is a big issue. In overfitting, the thing is that here you have the axis from the time, and here you have the axis for the error. Of course, at the beginning of the time, your error will be very, very high. And you will expect that the more time you spend training your network, the lower the error you will have. You can see it here. This is the training time. But what will happen in reality is that if you have a very low training error, you will have a big test error. So you may train your network and it will say, yeah, okay, I can classify it 100% with 100% accuracy all of the data. But when you give new information to the model will make so many mistakes. Why does this happen? It happens because we overfit our model. It's like, for example, when you try to learn something new and you only focus in some very specific detail of your task, it can be the case that when you have new information, you don't know how to do. You don't know how to solve the problem. If it's just a little bit different from what you train, you don't know how to solve it because you only train with one kind of data. So if we overfit our model, this is going to keep growing. So, for example, we train our model with this error. It will have like 0% of error in training time. But when we test it, all of these are misclassified. That will be way better with the first approximation. The first approximation had some errors in training time, but in testing time, it will be much better. So you have to remember that. Don't overfit your network. When you have data, you have to divide your data always to, let's say, 80% for training and 20% for testing. Never go for 100. So that was classification for supervised learning. For unsupervised learning, sometimes we have a lot of data, but we don't have much information of the data. Or maybe just so much that it will cost a lot of time to label the data. So we use unsupervised learning. In unsupervised learning, let's say we have houses. We know their size and we know the price. What we need to find here is this equation here, so that when we put new data, we can say, okay, this is very close to my equation in this point. So I guess the price will be this, or the size will be this. So this is how regression works. That was also supervised learning, I'm sorry. But for unsupervised learning, we don't give labels to the data. We just have like the normal data without any labels. And it's usually used for clustering. So we have to find patterns that we don't know, we cannot see them. The data is so much that we cannot go through all the data and see, yeah, this is this or this is something else. We have to give it to our model, and our model will hopefully find something that we can't. For example, a very famous example to demonstrate this is called the cocktail problem. It was presented some years ago, and it says that when you're in a party, you don't have any problems to focus in one conversation while you also hear the music, and while there is a car outside, maybe you hear a dog, that's perfectly okay. You can focus in the music, in a concert, for example, even if there is people talking, you don't just have an overload of information and die. You can absolutely process all the information, but the machine will not die, but froze and go like, yeah, this is too much, I can't handle it. And that's what was happening before. With unsupervised learning, this is solved because we give all the data and our model will classify it. So it will say, okay, the sounds that a baby does seems similar to this particular wavelength. And the sounds that a grown-up makes are like this other particular type of wavelength, and so on. So it can find patterns that it will be way too complicated for other kinds of applications. That was, for example, with audio, but you can use clustering for everything, many other things. This is an example with image recognition. So you have this cat, and you want to just extract the cat. Let's say the background is too ugly, I don't like it, I just want to take the cat. There are many ways to do that. In Photoshop, you can like select it and so on, but let's say you don't want to spend all that time and you just want to put it on your network and say, yeah, just give me the cat. So this is how it looks it was like 10 lines of code, so it's super easy. You give the cat, and it will subtract this. And how is it doing this? It will look pixel by pixel, and it will compare with their neighbors. There are other ways to do that, but this was the particular case. And it will find correlations of all the pixels. This network said, yeah, all those pixels seem to belong to the same cluster. So I think this is the cat. And this is what it gave me for the cat, and this is what it gave me for the background. So as you can see, it is a very useful tool for when you have a lot of information and you don't know exactly how to process it. So the last part of machine learning is reinforcement learning. This is very commonly confused with supervised learning, because in both cases, you know what you expect to have at the end. You know the expected output. But there are very big differences. Let's say this is an example from OpenAI. I don't know if you know it, but it's a framework to test your models for artificial intelligence. It's open source, and what it tries to do is just to give a framework for everyone to train their networks there. So in this case, they made this application, and this is the agent. This is what it's going to have the model. So this is our model, and they told their model, okay, so what you have to do is gain as many points as possible. That was all the information. This has to learn, okay, every time I've moved without the ball here, I reduce my points. And every time I hit this, I gain points. So with a lot of mistakes, it learned, okay, I have to hit the colors, and then I'm going to get points. And every time this falls, I'm going to lose points. It learned it by itself. So even if you know, even if you're checking if it's doing something correctly or not, you're not labeling the data. You're not explicitly telling this agent what to do or how to behave. You're just going to tell her, okay, or tell it, if you hit this, I'm going to give you a point, which is a reward called in reinforcement learning. If you lose, I'm going to punish you, which is the used term from reinforcement learning. So that's the difference. Let's say that you have a game of chess, and you want to approximate this with machine learning using supervised learning. Then you have to tell your model, those are the pieces, this is the chessboard, and you have to label the data for every possible decision. So you have to tell the model how each piece moves. Let's say the horse moves in an L, for example, you have to explain it, and you have to label every possible solution. In this case, with reinforcement learning, you will only tell the model what it means to win and how the pieces can move. That's it. You don't have to label for every possible movement. You don't have to create a new set of labels, which is much faster for some cases. It is recently used for robotics, healthcare, and smart cities, but you can use it for many different things. So it is really up to you. You have to see what is your problem and think exactly what is that you are trying to achieve. So, as I told you before, you have to try to avoid the overfitting. And to that, you have to classify your data in training datasets and testing datasets. So we usually give 80% of our data to the training dataset, and we reserve the last 20% to the testing. This is important because you have to reserve some of it, some of the data, you have to hide it from the network so it doesn't overfit. You should always avoid that your network knows all of the data, because even if you give the 100%, you will say, okay, this is all the possibilities, but it's never true. When you try it with some real new data, it's going to fail. So I'm going to show you now some case studies, some examples, so maybe it's a little bit more clear. I guess all of you know Netflix, if not all of you have it. And to me, I'm always so surprised how it gives me such an amazing recommendations. It really looks like it's the person who knows me the best in the world. And I'm like, yeah, okay, how does that work? So it is very complicated because at the time of this presentation, there was over 170 terabytes of data in Netflix, which is a lot. You cannot process that with normal computing. It would take so many resources. I mean, you can, but there is no real reason, but there are better tools to do that. Okay, so how does that work? Let's say Nancy has already her profile. She has seen already some movies. She has already rated some movies. So Netflix already knows some information of her. So this works with vector multiplication. So you have your vector, and to each element of your vector, you give it a value. Let's say in this case, the first will be for action, then drama, then romance, and so on. And then you have to fill the data of the vector for every user. So when you want, or Netflix want to recommend something, it's going to check the vector of that particular movie. So let's say that movie 1 has those values in their vector to know which kind of movie that is, if it's drama, if it's action, and so on. And you will have, in this example, 3 movies. So which movie would you recommend to Nancy if you already know what she likes? So for do this, it's simple vector multiplication. So you have in the top what Nancy likes, and then you have the 3 movies in the bottom. You have to multiply, like, for each element, and then make the sum of all of them. And then you can know with some certainty which kind of movie she would like. You may think this is easy to do because you can do it by hand right now, but you have to think how much data they have. And this is just a subset of how Netflix works. This is an oversimplification, so I can show you a little bit. But it's not just that. Netflix will always check how similar your profile is to someone else. So if someone else who has a similar profile than you already rated with a very good rating another movie, is going to put it in the vector, and then it's going to do more processing to see how similar you are. So maybe you would like the same movie. So this is how it works, basically. Like I told you, this is a simplification. All of the data that I show you is very simplified, but it's just to show you how the basics works. So like I told you, what I do basically is computer vision. So if you're interested in how computer vision works, how they recognize a face, or how do they know if, like the example that I showed you, this is a dog or it's a cat, of how Facebook knows to who you want to tag, we're gonna have a deep learning workshop later, like they already said. So we're gonna explain a little bit more deep into deep learning. So this was just machine learning, but the most biggest area of machine learning right now is deep learning. So machine learning is super big. One subset of it is deep learning that uses neural networks with very profound, with very deep layers. Neural networks are also not new, they're also very, very old, but they have the same problem as other kinds of machine learning. It was very time consuming, it was very processing consuming, you simply didn't have enough data. Now it's exploding because we have so many tools that can help us with that. So I'm gonna talk about that later. I'm gonna give you like a brief overview of what is deep learning. And then we're gonna use the knowledge, the information I'm gonna try to give you in the Intell SDK tools for deep learning and computer vision. So you will be able, we're gonna use the most common and the first program to do in machine learning is the MNIST, which is image recognition. So you will have the data set, you will train your data, and then you will test it, and your data will hopefully successfully tell you what that image is, which number it is, and so on. You're gonna see how much time it takes with different topologies of the networks that I'm gonna explain you later, and you're gonna see how much better it is if you optimize your network, because it can be very time consuming, but with some different tools, some of them, and the one that I know, obviously, is the one from Intell, we can reduce the time significantly. So we're gonna talk about that later. I hope you guys stay, and yeah, thank you.
In the Netflix data, was the data labeled in the vectors?
Yes, so I'm gonna go quickly about it, but it's labeled with so in this case, Netflix hires humans, which sounds weird, but hires humans to label the movies. So when you like a movie, it's already labeled by a human, which is always the difficult part of supervised learning. So far, humans have to do it. There are like some research that tries to say that, yeah, that's going to be solved. We're going to create other machine learning that's going to do that for us. But for now, this is the job done by humans. So each human will say, yeah, you like Twilight, that's a crappy movie, that's the classification of it. So that's how it's going to be labeled. Okay?
I had a question about overfitting. You say that you use 80% of the data for training and 20% for the data testing, but you can already overfit your algorithm with your model with 80% of the data. So what do you do, like, if you see that it's overfitted with during the testing phase? Like, do you?
Yeah, totally. You can overfit your data with even less than that. There is no like real rule on how much data you have to use. This is just what, let's say, all the academics have agreed for, just simplify things. But if when you test your model, you see that it has 100% of accuracy, which I'm going to do it in our workshop so you can see it. If you see that that happens, you have to go back and then you have to train your network again. With either you have to put more data or reduce the time of times that you're going to train it.
On overfitting.
Yeah, it's
Yeah,
on.
oh, sorry. On overfitting again, is there a way to efficiently know when to stop?
No,
So you just wait until it's too late, then you come back?
there is no way.
Okay.
Yes.
Thank you.
It's some limitations. Like I said, there is no real rule to know that. But yeah, you have to approximate it. At the end, when you do it plenty of times, you kind of get a feeling of how complex is your data and how much your data have. You kind of know how much you will have to train it. But
Okay.
yeah, it depends.
Thank you.
So you have talked about agreement in the scientific community. So I was wondering if there is an agreement about the margin considered to be overfitting or overgeneralization. Like in the scientific field, we say, oh, if it's not 5%, that's good enough.
So yes, there is, but I don't remember that exact value right now. So it exists, but I don't want to tell you a value that is not the right one. But if you can look in a paper, you will absolutely find it. There is one, yeah.
In the first example with the picture of the birds, the cats and the dogs, how do you map the pictures to this two-dimensional grid? What are the dimensions of this grid?
Yeah, that, like I said, is over simplified. In this case, I just made it like two-dimensional, but you can have like, okay, not infinite, but so many, like a very big matrix with so many axes. So this was just a simplification. That's not how it looks.
Okay.
So deep learning is using the characteristics of the data to classify them. And is it possible that the algorithm will find other characteristics afterwards to improve themselves?
Yeah, so this is that I show is machine learning. Deep learning is a little bit different. So it says something related to what you said. In machine learning, let's say typical machine learning, you have to specify a lot of values. But the one, because there are so many good things about deep learning, is that you have to reduce the amount of parameters that you have to specify. But I really think it's very important. We were thinking if we should go directly to deep learning, but it's very important to know how machine learning overall works so we can actually understand what are the benefits of deep learning.
Bonjour tout le monde, on m'a demandé de parler en anglais, so I will switch to English, but I can speak French as well. So I'm very happy to be here, thank you. Very happy to be here. It's the first time I come to 42, and so I'm glad to have the chance to meet you guys and to tell a bit about AI. What's next, in the sense that I'm going to talk about things that you don't often hear about in AI, because it comes from the world of fundamental research in AI, which is what I did in the past. Now I'm running another venture, something completely different. It's in video game. We are building a virtual world called Dual Universe. So it's a startup that I've created 3 years ago. It has nothing to do with AI, but before that, I used to be the chief scientist of a company that maybe you know by the name of Aldebaran, making a humanoid robot. It's been bought by SoftBank, so now it's SoftBank Robotics. And before that, I created and directed the research labs in AI also at ENSTA, which is another school of engineering school. So that's my background in AI. I did a PhD at Sony Computer Science Lab, where there was, this eyeball robot. Maybe some of you know about this very old robot. It used to be a dog. And there was a lot of fundamental research done there. So just to introduce myself, as asked, I'm an AI guy, but from the science side, deep fundamental research. And to clarify, what we're going to talk about today is the AI I know mostly, and in fact, it's going to be the last item that you see here. There are basically 3 ways to approach AI. So I want to clarify because AI doesn't mean anything. It's so broad. It's like when you say robots or things like that. It goes from cars to humanoid robot to medical robots. Those terms are too generic. So let's narrow down a little bit the topic. To me, there are basically 3 ways to approach AI. The applied AI, which is what you hear most about. We just heard about just a minute ago. It's the AI that is concerned with solving engineering problems that are well defined. You try to solve the problem. Whatever works, it's going to be fine. And so you have neural networks, you have more traditional symbol processing things that are used in this domain, or anything, actually. It could be something not at all funky, just a clever algorithm that does the job. And then you put a stamp AI, and you raise funding, and you make a startup in Silicon Valley. That's very good, very good. The other domain is biology inspired. So the people working on that, they are concerned about trying to model neurons, basically, at the most precise level, to the chemical level where everything is happening in the neurons. So they want to make a perfect model in a computer of a biological neuron. So you have mostly, this big project, a big brain project that have been funded recently. So this is meant to explain the living by creating a model of it and running this model and seeing that you have a brain that works the same way as the real brain. Doesn't mean that you will be able to explain anything. If I create a brain in a computer that is working fine, what do I don't necessarily understand much better what's going on inside his brain, right? Because it's probably the result of millions of interactions that I'm unable to track. So this approach is very specific to trying to model the biology, but that's not what I'm interested in. I'm interested in the last domain, which is general intelligence, AGI. It has different names, or strong AI. Those domains that are concerned with not only reproducing the aspects of intelligence, but also giving a model of it. So trying to come up with maybe what could be called a sort of theory of intelligence that describes what's going on in an intelligent brain, because that's the only intelligent thing we have to observe at the moment, but try to figure out what are the mechanism going on, the higher level description of what's going on in this brain, which happens to be implemented with biological neurons, but maybe it's not that important. Or maybe it is. Nobody knows. That's make things clear. No one knows how to make strong AI. So I will show you my opinions, my view, my church, I would say, in this field. But you have to criticize. You have to be searching for things. Nobody knows. Nobody has the right answer. So you can question everything. This is science. Okay. So what do we have today in AI? Mostly 3, it's a bit of history, right? What happened in the domain of AI? 3 main things that happened. First is it started with the world of logic and symbols. This H9000 computer in the movie 2001 is exemplifying this very well. You have a machine that is all about abstract symbols, logic, chess playing, this kind of things. This vision was in the 70s, all the craze with things called the expert systems. You may have heard about that. It's still in use in the industry. It's very useful. It has a nice property. So expert systems are just computing logical relationships between statements, and they have some rules to deduce facts, and they can run that in series so that they come up with conclusions and find out about questions you can ask to the system. Very interesting. An interesting property that doesn't have deep learning, for example, is that, at least at the moment, is that these systems are able to explain why they came with a certain conclusion. So it's very useful. They can tell you, well, I think that because la la la, and you have a logical string of, stream of deduction. Very interesting. Not so much in, it's not à la mode anymore, but it's still something that was extremely successful. A bit later in the 80s, there was a lot of activity around neural networks, biological models, or simple, more classifier. I mean, they don't care that it's biologically plausible or not. There's a vague inspiration, but basically it's just a mathematical tool that you've been presented just before. It's all about classifying and segmenting large spaces with hyperplanes and things like that. So this gave interesting and very encouraging results, but we didn't really know how to increase the size of those things so that they could tackle more complex problems. And then came the new generation of machine learning algorithms, mostly deep learning, in the 2000s and 2010s, that basically, together with the increase of the CPU and I would say GPU power that was available at that time, plus some clever tricks to handle the increase of complexity, managed to actually get incredible results from this second approach. The deep learning is the big thing, but other things also are very promising. So that was and is the story of AI so far. The problem is none of these approaches answers the problem of the acquisition of intrinsic meaning by the machine. So none of those direction is really tackling what is probably the core central problem of AI, which is the capability of the machine to acquire meaning for itself. I'm going to quote Stephen Harnad in the 90s, who framed this core issue in a paper that is famous, the symbol grounding problem. So you have symbols, why not? The first wave I presented, expert systems, but they are not grounded. They have no meaning. It doesn't mean anything for the machine, what it's using. Let's talk about symbols, for example. If you manipulate symbols and you change them with some rules, if your father is, the father of your father is my grandfather, so if I know the names of those guys, I can deduce who is my grandfather, because I know my father. Well, these kind of things. This is meaningless, because the machine is just processing strings of, the letters that doesn't have any particular meaning. To give you an example, if I give you a book, not a book, a dictionary of Chinese. Most of you, I suppose, don't speak Chinese. I give you this dictionary, and I ask you to tell me what's the meaning of a particular word in Chinese. So you will open the dictionary, pick up the word, you recognize it, and then there's another stream of Chinese words. You don't know them, so you carefully write them down, and you look into the dictionary, each of those words, right? And you continue like that. Of course, as you guess, I mean, you will not be able to understand the meaning of the first word I asked you. So you're running in circle with something that has meaning only because it is taken as a parasite to the meaning that are in our heads. We know what the series of letters that are T-A-B-L-E means, table. We have a meaning for that. We know what is a table. We have interacted with a table. So whenever the system is outputting the word table, it's okay. We know what it means, but the system doesn't know at all what it means. You could replace those letters with random things. As long as it's consistent, it will be happy. In the same way, if you look at deep learning, it doesn't understand what it's processing. There's a lot of examples where you can show, so these famous images of a cat and a dog, they are very famous, and they're extremely accurate. They can do a fantastic job at determining whether a given image is a cat or a dog. But there's this adversarial examples that can be built very easily, where you have a choice. You can have either an image of a cat that you disturb slightly by adding a few pixels. If you look at this image, it's going to be the same image. You won't even notice, actually. But then it will completely screw the recognition for the deep learning system. It will start to say, well, this is a car, obviously a car, with very high level of, confidence. And the similar type of example is that you can forge an image that will be completely meaningless. You look at it and you say it's garbage, it doesn't mean anything, and you give it to the system and it will tell you it's a cat with a very high level of confidence. The system doesn't know what it is processing, what's the meaning of what it's processing. And in fact, I'm using this word, I'm a bit cheating because I assume you have an intuitive definition of meaning. And if I were to ask you, what does it mean, the word meaning? This is the problem, the meaning of meaning. This is one of the hardest problems of AI. So there's a good chance that the definition you would come up with is probably going to be naive and not going to capture the complexity of this core problem, which is to create machines that build meaning, whatever that means. I'm going to give you a definition that is the one I stick with, but whatever. We need to make machines that are capable of creating things inside their internal representations that are meaning, so that are corresponding to this definition, and they're capable of acquiring these meanings by themselves. And that is the very hard problem of general AI. So that's what me and hopefully several others believe meaning could be. So I'm going to read this. Meaning emerges as invariance in the tight coupling between sensors and actuators data flow. What does it mean? It means that, it's difficult to talk about meaning because I keep saying, what does it mean, as I'm talking about meaning. Okay. But anyway, so this definition is saying that what actually is meaning comes from the tight interaction between your body, which is specific to you. Nobody has the same body. And the way, the fact that you move your body, so you act in the world, is changing your perception. And there are some invariants in the way those things can be coupled. And these invariants, the things that are stable somehow, you can extract them and they become nuggets of meaning. So things that are stable enough so that they are worth memorizing and putting in your classification of things that exist. If I talk about the meaning of flat, the meaning of flat is if I as a baby, I learn the world around me. I will come back to this about babies, it's essential, but I'm calibrating the meanings of the different meanings. I'm touching surfaces like that. And actually being flat is a complex interrelationship between the value of my motors on my hand, on my arm, the fact that the pressure sensors are basically at equilibrium, and also I could correlate some visual flow in my retina that corresponds to the movement of my hand. And it's very, very different when it's flat than anything else. When it's not flat, there's a different profile that connects the way all those things vary. So the sensor and the actuators, the perception and the action are bounded into something that corresponds to flat in that particular case. I'll give you this as example as a straightforward, example of a thing that connects motors and actuators, but the same reasoning can go with colors, with notion of space, and basically anything that sits at the bottom of a hierarchy of more and more abstract things that are built on top of those grounded fundamental meanings that are invariants, not only of the world around you, but also, but mainly of the interaction between you as you are and the world around you. Because we all have more or less the same body, we come up with the same, type of meanings, same lexicon of meanings inside our heads because we have the same kind of bodies. But if we were a spider, we would, or or a fish, we would build very different types of meaning. I'm absolutely sure that those animals are building meaning in that sense. So creating those invariants that corresponds to a signature of how their particular body is capable of influencing the physical world around them. And even the most complex mathematical concepts that you can think of, you can deconstruct them down to very basic and sensory motor primitive meaning that you can relate to. When I do mathematics, so and as you, when we talk about derivative or things like that, the meaning of those things, if you're good in mathematics, you see those curves and you see the slope and it's slopy. You know, maybe you think about when you do biking and something. There's something physical about the derivative of a function. If it's not for you, it means that you're probably not good in mathematics because you're just doing syntactic, meaningless succession of transformation that you learn by heart to do the derivative of a function instead of seeing through those lines the meaning of it, which is usually quite obvious. And then you go into more complex mathematics and complex notions and you get more and more far away from the immediate perception and action, you know, meaning, but still you can reconstruct the building. So if you think this is true, then you have the clear consequence, which is that general AI needs robotics. There is no such thing as meaning without a robot because you need a body to be able to establish the correlation between your action and the perception and everything I said before. Without the body being a pure observational machine that looks at things, like deep learning, doesn't get you access to meaning, just classification. Classification doesn't bear necessarily meaning. And one of the problems is that there are many ways to do classifications. So one way to constrain that, we will see in a second, is to synchronize your meanings with the other agents around you, the other humans. And that requires interactions and things that are not part of the agenda of deep learning or these expert systems or all these previous ways of doing AI. So you're a robot and you're about to build meaning by interacting with your body, with the physical world. How does it look for you as a robot or actually as a baby? It looks more or less like that. You get some sensory channels, some motor channels, and there are values that change over time. It's a total mess. It looks like that. This is an example of an experiment that was done pretty recently with a robotic arm that is going to do what is called motor babbling. You know, babbling is when the baby is blah, 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 blah. It's not only babbling with words, it's also babbling with its body. If you see a baby is usually moving like that, it's actually, we believe it's actually calibrating its perception of space. So the space is something that has a meaning, which is the correlation between your body and the way the environment is going to respond to you. And after thousands of iterations, you can start to build a map that gives you a notion of proximity, of something up, down, on the right, on the left, and those things acquire meaning. It's very meaningful to be on my left. I know how to do this. I know, you know, these words, we will get to the words after, but these concepts, they are grounded into the interaction between the robot and the world. Okay, so now we come to the problem of synchronization, because with what I just said, you have a bunch of agents, they have interacted with the physical world and they grounded some invariants that represent how the body is capable of changing the world. It's more or less the same for the most, primitive, obvious things, but when it starts to be a bit more elaborated, every agent is going to go into different routes. So if you take an agent in isolation, I say agent because to me it's like baby or robot, same topic of research and study. So the agent is going to build these meanings. Another agent is going to have some meanings in common, fairly similar, but might actually, because there's a bit of randomness and uncertainty, might actually ground certain meanings that do not exist in the other agent head, and you have a problem of synchronization. if you want to be able to communicate, you need to somehow align the meanings and select those that are common in your in the other agents, and take out those that are not. You have to perhaps work hard to try to figure out new meanings by experimenting, because obviously you don't have that particular meaning in your head, so there's something to learn, because everybody is using that meaning, so what is it? So you start to experiment and select which one is going to be efficient for you to communicate with others. So there's a phase of alignment where language is, of course, essential, because language is a way to take little labels, words, that you put on your meanings. So far, your meanings were kind of abstract things in your head. Your brain is optimized to store them and, you know, recognize them and identify them. There are invariants, la la la. Okay, but now you are going to be able to put some labels on them. Which is, by the way, exactly the same mechanism. Those labels do not exist, of course. It's just another invariant as well. But anyway, make it simple. You put those labels, and you start to use them. You start to use a word to designate an object, for example. And there was a fantastic experiment called the Talking Head experiment, where you had two agents, two cameras, simply, that were looking at a whiteboard. So this was a very simplified experiment, and so it doesn't include the body interaction, and the meaning was more or less automatically extracted, because the point was to work on the synchronization, so the emergence of language. And so those agents were just keeping track of a lexicon of words to describe certain meanings that they extracted. And they were playing language games, a simple game which is called a guessing game, where, you know, I look at a certain shape, and I'm going to use a word to describe it, and the other agent is hearing the word and have to guess. It has to guess which shape I'm designating. So then it points and say this one, and it's either a success or a failure. If it's a success, both agents reinforce their association between that word that was used during the game and the internal meaning they have. Might not be the same, actually. So there might be, you know, unfortunate misunderstanding that works. And in the same way, if it doesn't work, they will lower the link. If it's going too low, they just discard it. So there's an evolutionary dynamics going on with an evolutionary pressure, which is basically the communication success. So things that are more successful to communicate gets promoted. And this, after a few thousands of iterations, comes to with many agents. So these are used by virtual agents that embodies into those cameras. So you have a large population, actually. And after a few thousand iterations, they synchronize their lexicon. So they come up with a language. They have a language, and they are able to play very efficiently. And now they know how to designate the red thing on top of the blue thing, or the square thing that is near the triangle. And they have developed their own way of saying that. And there is no... the next step of those research is about grammar, how they disambiguate. For example, when these things are moving, there's action, so they start to talk about actions. The particular way you disambiguate who is the actor, who is acted upon, they choose different strategies, a bit at random, and then the evolutionary dynamics will select something that works for everyone. Could be sometimes the order of words, like in English, or preposition, or the way you end the words in German, or things. So you have different strategies, no matter what it is. If it gets you to get a good communication, this is going to be selected by these agents and crystallize into their language. Very, very interesting experiment. So that's the problem of synchronization. You acquire meaning, and then you have to synchronize them, and that helps you to sort in this ocean of possible meaning. I could come up with a meaning to describe a particular square thing with a hole in the middle and some. I mean, I could have a meaning for that. If we were living in a world where this kind of shape were extremely important, I don't know. If you see it, you get food, or if you don't, you die. Okay. I can tell you this will have a name. So in every possible things that are in the world of meanings, we select those that are more efficient to communicate because they are related to what we do, and we communicate because we are social agents. And so that comes to the next one. that this experiment is important because it crystallizes all the key important things in AI. The symbols that are emerging to the words or the grammatical conventions are socially grounded. It is shared, so they have the same one, which is not at all obvious to achieve. It's the dynamics that is underneath is an evolutionary dynamics, as I said. They are grounded in the environment, of course. So because it's based on the definition of meaning I said, if you change the environment, the perceptual environment, or the body of those robots, they will come up with new meanings, and they will readjust. Typical example, you shut down their color camera, put them to black and white, and all the colors are going to disappear from their vocabulary and be replaced by shades of gray. New words to describe shades of gray, because that's useful now. It was not before. And the third thing is that those symbols are grounded in the task, in the context, so in this particular experiment where it's a little bit more sophisticated, but I don't have time to go into details. So it's grounded into what we want to do. And we as Homo sapiens are very good at forging plans all together to get things done, which most animals cannot do or in a very limited way. And we are able to do that because we are able to synchronize our meanings. We are able to create a language so that we can talk about things in a way that is meaningful because it relates to our capability to interact in the world. It's not abstract. It's grounded. So these are probably very, very important things to include in any research that is dealing with AI in a strong sense. And that, to conclude, that gets us to a field of research which is called developmental robotics. I'm going to quote the great Alan Turing, who perhaps first, I mean, it's usually quoted as the origin of this idea, but I think it's a very simple idea that many people had also. But I quote him to say this intuition that if we have to build up, the meaning of everything from the ground up, starting with the building space representation and calibrating your body. Actually, the starting point for AI is more in the infant and the baby than it is in Kasparov or the champion of Go. This is where we should start. And so instead of getting to an adult mind, the way to tackle the problem of AI, to start with a baby that is going to acquire competencies, social competencies, physical competencies, cognitive capabilities over time. And the good news is that there is a whole field that exists for many years now of study of how this is happening in humans. It's called developmental psychology, with people like Piaget or Tomasello, who have studied, how infants are acquiring language or acquiring basic cognitive skills about space, about time, etc. They also worked a lot with chimpanzees to understand how they do it also, and what makes it obviously different from us at some point. There's a whole lot of research that exists that we can look into to actually give us insight or even landmarks, like in good science, where you come up with a theory, and then you bring your theory in front of nature and you say, is it right or wrong? This is the blessing of physicists that we don't have in AI. It's not easy, to test your theory of AI. Well, that's maybe a way to test it, is that you compare how your baby robot is growing compared to how the human robot is growing. On the way here, to come here, I was listening to a talk that emphasized the fact that, the vision of babies is extremely blurred in the first month. And they don't see much. The resolution is very bad. And you start to think that this is actually very important to be able to scale up in your skills of understanding vision. You start with a very low signal, very low dimensionality signal. You acquire basic things, and then the signal gets a bit better because your eyes mature, and then you start to build up more representations and more capabilities. So you see that even on the physical side, the fact that you have a developmental approach might be fundamental to stage the levels of learning of your system. Because if you put the system full-blown with a high-resolution image, it's too much data, it doesn't know where to go, it doesn't converge. Or it would take maybe thousands of years or tens of years. right? So this is a very powerful inspiration, and it started the field of developmental robotics. So that's the typical illustration, I would say. Human and robots at the same level, actually interacting with each other. It's very interesting to get a human interacting with a robot and do experiments with that. They love it, of course, and it's very insightful. There's tons of things in developmental robotics. I just wanted to highlight one example, which is extremely interesting, and which I think is one of the other very difficult things in AI that needs to be addressed is why do machines what would they do something at all rather than nothing if all their physical needs are satisfied? The battery is full. If you take a human, you give him food, everything is fine. He knows that there is food in the fridge. Most humans will not sit idle until hunger comes again and they go to the fridge. There's something that gets us to do things even when we don't have to. So it's usually you hear, well, no, it's okay. We're just basically dealing with our physiological needs. But no, there's something more. Of course, we do, and it is driving our lives in many moments. And it's but still there's something more. And this has been coined as intrinsic motivation or artificial curiosity. You can give surprisingly simple mathematical descriptions of this concept of curiosity, which is a drive to try to decrease the rate of prediction error. So your system is predicting all the time what's going to happen, and it's trying to decrease the rate of error. So if the rate is very high, because it's too complicated, you keep making mistakes, and it's way beyond what you can actually learn, you're going to get bored because your rate is going to stay high. And you're not going to stay in this situation. You're going to move on to something more rewarding, where you have a chance to actually increase your rate. A chance to decrease the rate of prediction error. In the same way, if you are in a situation that is too easy, you win all the time. There is no error. Your prediction is extremely good. Same problem. Your rate is not going to decrease. It's low and it stays low. It's boring and you change topics. So there's a sweet spot between something that is too difficult and something that is too easy, where you like to be. And this is what this simple formula is actually modeling. And if you apply it to a robot experimenting in a baby setting like that, you'll see the playground experiment. It's very impressive experiment also that showed that this simple mathematical formula with a bit of wiring on the engines and so on, is capable of actually getting this robot to explore his environment in a staged way. So it's going to explore first his motor capabilities. He's going to be interested to see that this is surprising, and then we don't hear it and it's too short, but after that he will start to emit sounds and see how the other robot is responding to it. So we'll gradually explore more and more complex situations. And that's very interesting because it stages, the steps of what you're going to learn, which is an important thing. If you, as I said, if you tackle the big problem immediately, you won't be able to learn anything. So this simple experiment is based on this artificial curiosity criteria, and it gives very good and interesting results that have been pursued by the people there for several years now. So I'm going to conclude not explaining this horrible big slide. I just wanted to show you this slide because this was the research program I studied at the AI lab at SoftBank. So you see that this part is structuring perception layers. This is where you find deep learning, which is a fundamental breakthrough that helps us to solve this thing in an amazing way, and which, by the way, has tremendous commercial potential. So it's true that if you want to invest yourself into a domain, this is a very good one to get a good job. But from the perspective of research towards general AI, this is just the first layer, and then you have all those things that are difficult. Well, I mean, in my lab, some other people will have other things, and this is research ongoing. Nobody knows. So you have different opinions, different strategies, etc. I just wanted to show this is just a part of the story. So deep learning and AI, key technology with huge business application, is going to change our lives. It's going to have a big impact. It's worth investing in it. It's a key stepping stone towards AGI, because we need these tools to be able to tackle with the huge dimensionality of the signals that the robot is getting. But it's not the whole story. So that's what I wanted to tell you today. Thank you.
Yes, question. Wait, do we have another mic somewhere? Okay. Just pass it behind you. I think somebody back there.
Is it okay if it's dual universe related, or it should be more about the conference? I was curious about the languages they are using to build this amazing game. Like for the server, for the graphical aspects.
You're talking about dual universe?
Yes.
Ah, okay.
Just.
Sure. Well, so what was your question exactly?
Which language you are using?
Which language? On the server side, we're using C++, which is a very bad idea, but we had no choice. We started with Scala, but which is a good choice. But we had issues with the interface with C++, which is living on the client side. So anyway, to make it short, we went to C++, but we use a library which is called libcaf, which is implementing a paradigm called actor-based programming, which is something you find in Scala with the Akka library, or more historically with Erlang, which is the way you're going to survive the situation, because we are using very high-level things in C++, and so our server is stable because of that. I hope that answers quickly.
And for the graphical aspect?
We use Unigine as a renderer, mostly.
Okay, thank you.
And that's a Russian engine.
Yes, I had a question about the slide where you had two robots with triangles and, well, not triangles actually, with volume 3D. And I'm not sure if I really understood what was going on about there. It's, there. Yeah. You let them interact and they kind of imagine in a language describing this environment, this specific environment. Or what do you first give them? Words? Or they invent the words or sounds? Or didn't I understand?
It starts in all these experiments. There is action going on in front of the robot's eyes. So there are things that are moving. Usually they are colored, so it makes the perception easier. But there are some actions going on. Things that are getting close to each other, things like that. And so the system has first to create, as I said, some invariants. When things are getting closer, there's a certain thing that decreases, which is the distance between for say, the center of gravities. And this profile of decreasing is something that you could recognize in many, many situations, and you label it. So there's a first phase, which is to observe things and try to find invariants, things that are not changing. And the fact that you're also acting is important, because you're not just passively looking at things moving, you are able to actually do those things. So you create invariants not only in what you see, but in the correlation between what you see and what you do. So this is sort of abstract mathematical spaces where you find these things that are always the same. I mean, you find them many times in many situations. So you then are able to upgrade them to a status of, yeah, you're interesting, and then you put a label on it, which is a random series of syllables, for example. In reality, what happens is that it depends on your vocal apparatus that evolution has made better and better as communication was becoming more and more important. Humans were probably selected for better capabilities to express a wider range of communication. But you are doing with what you have, and you babbling as a child to blah, 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 try to see what is the space of things I can say. And then you use those things in those experiments, at least randomly. In reality, of course, there are never cases where you have a community of humans, infants that are separated from the rest of the world. So you arrive in a culture that already exists with an existing language. And what happens is that you fine-tune your babbling to what you hear, so that what you babble sounds like the things you hear, and you have an invariant here again. So you use those syllables that you are capable of producing and also hearing as building blocks to create random words. And you try them. And of course, it doesn't work until you find the right spot where you are pronouncing something that the other agent is recognizing. And it does the other way around. It's taking the sound and tries to look, I'm going to use images, but he's going to look in his library if he already has a sound like that he's using himself. If so, then he's going to look down at the meaning that is associated, this invariance, and then he will be able to recognize the action that you're talking about, for example, because in the current stage, when it's looking at what's going on, he already spotted that this invariant was present. So he might say, oh, yeah, I agree, this is happening, for example. See, the chain of action is kind of, there is a slide at the end. Well, it's going to take too long, right? But okay, there are more things about that. I recommend this book, which is probably just before, yeah, that one that is the bottom. If you want to read about this, it's fascinating.
Okay.
Last question before we all die over. Use the break. I don't know how long.
Yeah, it's fine if you want to keep discussing with pleasure.
I think
it's all right.
Hello. So if you say that meaning is always based on something physical, even mathematics, does it mean that we will never have like robots with feelings or stuff that are not physically related, or philosophy or humor? Or
Alors, there are different things in what you say. Feelings are physical because, you know, when you have a certain feeling, your brain is generating some I would say hormones and things, so that there's a physical response that matches your feelings and your emotions usually. So it's something you really feel in your body. Now, whether it's necessary for a robot, that will, I mean, there's a whole set of research on emotions, whether they are, to what extent they are useful, to what extent they are providing shortcuts, pathways, so that you can do things faster without having to go into complex thinking. The role of emotions in as a proto-language that is a given from evolution. Once you are, when you're a child, a baby interacting with your mother or your father, how much this is important to actually help you to bootstrap. And I don't have the answers. It's a complex topic. The other things you mentioned was about philosophy and let's say higher level, you know, artistic activities, I suppose. I think these things, as abstract they may seem from the outside, I think you can deconstruct them down to physical, concrete things. Even the most abstract thinking, you know, even if you're considering spaces of dimension pi and things like that. Okay, so you can always go down. I think, you know, go down to physical, basic meaning that are actually used as building blocks to construct these abstract things. We could take a philosophical book, even the most obscure, and try to deconstruct that. And there are lots of images, there are lots of metaphors where things are next to or comparable or on top. Yeah, next to, on top, these are physical things. You know, these are all things that we use as we talk, as a way to make it easier for us to be understood. We resort to spatial information, temporal. You know, this is everywhere in every thought we're expressing, including the most abstract one, I think.
Sorry, guys. I mean, I guess you guys have a bunch of more questions, while the same amount of you guys are hoping for us to release you out of this a warm room. Jules just told me this university has AC everywhere, except for this room, which very interesting. But anyways, Jules is going to give you the further agenda where we're going to meet upstairs in a bit. So Yeah, first of all, thank you again, Giuseppe.